Hi everybody, my name is Tovio Roberts and this is the study hall stream for Galvanize DSI Prep, and we're just getting started. I haven't done anything yet. If you are tuning in and you are in our Slack org, please just drop a quick emoji in the Slack thread. Feel free to ask any questions. There's already a question coming in, which is pretty cool, and I'll start working on that in just a second. Let me just do one thing first. Okay. All right. So let's look at this question. Confirming question on how to read console output of def binary sampling dictionary code. Parameters are 8 bits and 1,000 samples. You read 1 to 21 as one success occurring in 21 of the 1,000 flips. You read 0 to 4 as 0 successes in 4 of the 1,000 flips. Yes. Short answer, yes. Let me. I think you actually slacked this code to me earlier. So. If I'm not mistaken, I'm going to go ahead and copy this code and throw it into here so that just so we can talk through it a little bit for anybody who is unfamiliar with what I'm talking about. Make that a little smaller, fit a little bit better. So I'll just go ahead and trace through this really fast, and we'll go from there, and I'll clarify what is meant by the output that we're seeing. Okay, so initially we've got this get bit, and get bit is just going to get us a 0 or 1. We've got get list of bits, which is going to get us, well, by default, 8 bits, right? N is 8, and we're getting a bit for every number counting up to 8. So 0, 1, 2, 3, 4, 5, 6, 7 is going to be 8 bits total. We're returning that as a list. We're constructing that as a list comprehension instead of with a accumulator in a for loop, but effectively that gets us the same result. So here in the binary sampling dictionary, we're putting together if you think about a sampling process, right? We're sampling 1,000 times from get list of bits, and we're putting the results in a dictionary. So for however many times in num samples times, right? Num samples is 1,000, so by default we'll do this 1,000 times. We're going to get some binary from list of bits. This is going to be just random ones and zeros. By default, of course, that's going to be 8 bits. So we're summing that binary and dropping that into this variable k, or representing it, pointing at it from this variable k. So if we have 4 ones out of 8 ones and zeros, k is going to be 8. It doesn't really matter what order those are in, right? It could be 1, 1, 1, 1, 0, 0, 0, 0, or it could be, 0, 1, 0, 1, 0, 1, 0, 1, right? So if we're thinking about this, this is directly related to a binomial process, right? This is there are all these different permutations that lead to a count of 4 bits, and so that's what we're getting here. We're getting the sum of the bits in that binary. And if k is not in the dictionary already as a key, right? So we're checking to see if k is already a key. I like that this says Tovio's way, because I tend to initialize the key with the value 0 and then increment it by 1. The way that you more often see it is that if it's not in the dictionary, then we load it into the dictionary, right? We set the key to 1. If it is in the dictionary, we increment it by 1. So effectively the same logic as to the way that I tend to do it. And then we traverse this. So for a key value in the sorted binary sampling dictionary, samples 1,000, of course, .items. That allows us to break the key and the value out into a tuple. We're printing the key and the value. So let's go ahead and see what that looks like. So we have that here, and I can just grab this like this, and maybe we can take a closer look at it. Okay, so looking at this, out of 1,000 trials, a way that we can interpret this, let me be clear, a way that we can interpret this is out of 1,000 trials, we had a sum of 0, so we got all zeros. That happened 3 times, right? That happened 3 times. We got a sum of 1, so 1, 1, spread across those 8 bits in some way. We got that 29 times. We had 2 bits spread across 8 trials, or 2 ones spread across 8, bits. We got that 85 times. And given that this is 8 trials, right, or 8 attempts at getting 1 or 0 with 50% probability, it shouldn't be too surprising that we got 4 the most times, right? So we got 4 302 times out of 1,000, and we have a reasonable symmetry as we go away from 4. Of course, we're not going to have perfect symmetry because this is a sampling process. It's going to vary every time. Something that we could do, and this is something if you're in the premium prep classes, or if you've taken premium prep before, you've probably heard me describe this process. We could sample the binary sampling dictionary another 100 times or another 1,000 times. So we could construct that binary sampling dictionary, however many times, 100 or 1,000, or some other number, and we could average the values associated with each key, right? We could do that, and that's going to get us very, much closer to the theoretical distribution, or the theoretical counts distribution that we would see if we generated those counts from the actual binomial PMF, as opposed to what we're doing here, where we're sampling and determining the counts. If we use the binomial PMF, we could populate a dictionary with the keys as the number of successes that occur, or the number of 1 bits, and we could multiply the probabilities associated with those by 1,000, let's say 1,000, and that should get us the theoretical counts, what we would actually expect, and not what we're observing when we sample. So I think that answers your question, right? That's, do you read 1, if 1 is associated with 21, as 1 success occurring in 21 of the 1,000 flips? Exactly that, yes. Okay, so there's another question here. And if there's any further questions regarding this code, feel free to ask, and I can jump back to it before moving forward. So there's a question here on total probability from the conditional probability section. So you got to the second question and realized you were lost. That's what I'm seeing. And so this is okay, so the question, let me snag this question, and likely instead of doing this question, I'm going to look at a different question, just because we don't have that many questions in total probability, and it does come up quite a bit. So I don't necessarily want to solve this for everybody offhand, but let's look at the problem and start thinking about it. So consider the following question. The probability that an adult who is at least 6'6" tall played basketball in college is 40%. And the probability that an adult who is shorter than 6'6" tall played basketball in college is 3%. What is the probability that a randomly selected adult was on a basketball team in college? Okay. Do you have enough information to answer this question? So that is the first part of this. And I can answer this offhand, and then we'll look at the second question, which is, I believe, where you are focused. So, so we can answer yes or no here. Unfortunately, the answer here is no. And the reasoning, if we break this down, I'll go ahead and kind of put this up in the right so we can reference it. So the probability that an adult is who is at least 6'6" tall played basketball in college is 40%. So yeah, this is interesting. This is the probability of an adult greater than 6'6" played basketball. That is 0.4. Okay, and then the next part is oh, you know what? Let's think about this as being conditional probability. So we could call this played basketball given being greater than or equal to 6'6". Oops, I just 6'6". So that's 0.4. The other piece of information that we're given is what is the probability that a randomly selected adult the probability that an adult who is shorter than 6'6" played basketball in college is 3%. Okay, so probability that they played basketball given shorter than 6'6" is 0.03. Okay, and what we're being asked to calculate here is the probability that a randomly selected adult was on a basketball team in college. So we're asked to determine the probability of played, there's no dot over an A, played basketball. That's the question we're being asked. So what we need to know to answer this question is, well, we need to know we need to know a couple things. We need to know the probability that somebody is greater than or equal to 6'6". And we don't know that. So this is a thing that we cannot determine given the information that we have. It's not given. So with that, that leads us into the next problem. And if I go ahead and put no for that law, that Q1, then it's going to give us some information that it will help us forward. Okay, so the information it's giving us is that very probability, right? That's going to be probability of height being greater than 6'6" is going to be 0.02. Okay, so now we've got a little bit more information to work with, and we can start considering this second question, which I will copy so that we can take a look at it. Okay. Based on the information from the explanation of the previous problem and the additional information that 2% of the adult population is 6'6" or taller, calculate the total probability that a randomly chosen adult has played college basketball. Okay. So let's kind of break this down. And if you're in the premium prep, we're going to have a conditional probability day where we go through a bunch of these kinds of problems. Well, we'll go through a couple total probability problems. Mostly we're going to be going through, what do you call it? We're going to be going through Bayes' theorem problems. But most Bayes' theorem problems underneath the hood are really total probability problems. So let's kind of deconstruct this a little bit and see where we can get with it. All right, so I'm covering up a little bit of information here. Okay, so played basketball given being greater than 6'6" is 0.4 probability. The played college basketball being less than 6'6" is 0.03. So where we want to go with this is, well, let's consider the complement first. Let's put down all the information that we actually have at our disposal. The probability of being shorter than 6'6" in this problem is just going to be the complement of the probability of being taller, or at least as high as 6'6", which is going to be 0.98. Okay, so from there we can apply the law of total probability. All right, so we're looking at this question at the end of the day. Played basketball. Played basketball is going to be a composition of a couple things. It's going to be the probability of, well, it's going to be this first probability, and hopefully I don't run out of room. Let me change colors to delineate this a little bit into red. So this is going to be the probability of, I'll just put BB for basketball, for playing basketball, being greater than or equal. That's a little hard to see, but yeah, I'll just do this. I'll just do the whole thing. Okay, so it's going to be that multiplied by the probability of playing basketball, which is 0.02. The probability of being taller than 6'6", right? So this is the probability of being greater than or equal to 6'6". We're composing this with, and I'll do it on a new line because I think my face might block this out, the probability of let's see, played basketball being less than 6'6", and we can multiply that by the probability of being less than 6'6". And so if we were to fill these in, and maybe I'll just make a little more space for myself up here. So I'll continue up here. If we were to fill this in, we've got these values. This first value is 0.4, right? I just erased it, but it's played basketball given being taller or as tall as 6'6". So that's 0.4 multiplied by the probability of being shorter than 6'6", which is, probability of being taller than 6'6". Sorry, looking at the wrong one, which is 0.02. and then that is composed with probably playing basketball if you're less than 6'6", which is 0.03, multiplied by the probability of being shorter than 6'6", which is 0.98. Okay, we can throw that into a calculator, and that is going to be 0.4 times 0.02 plus 0.03 by 0.98. And it looks like there is a 3.74 probability of playing basketball. So the probability of playing basketball, in this case college basketball, is 0.0374. And to be honest, these kinds of problems, you have to do a bunch of them. Not to, I hope that's not discouraging. They become rather easy after you practice them a bit, but they're a little counterintuitive, right? Because you have to really discern what's being asked, and I think that's not always the easiest thing. So, when you start thinking about this, like, well, what information is missing, and how do you compose this information? The probability of playing basketball is going to be a composition of the probability of playing basketball given that somebody's taller than 6'6", multiplied by the frequency of people being 6'6" tall, and then you compose that with the probability of playing basketball given somebody is shorter than 6'6", multiplied by the rate of people being shorter than 6'6". So that sort of like, pulls those pieces together and recomposes the probability of played basketball. When you're intersecting probabilities, you can just multiply them. Well, notice what we're doing. There's I'm not totally sure I get the question, but notice that we've got the probability that somebody played basketball if they're, taller than 6'6", multiplied by the rate of people being 6'6", and then we're composing that here. So we can, yes, when we're intersecting these probabilities, we're multiplying them. Yeah, we can think about this first part as being, or we can think about this whole thing as being extrapolated from an intersection, right? And I'm not sure exactly how our lesson goes over that. I think there's a really nice intuitive way to break that down. And you know what? I could go through, if it's worthwhile for you right now, I could go through and kind of extrapolate this out. I think it is actually kind of fun to do so. You'll see it again in the premium prep class, but I could take a few minutes right now to do that. So let me just do that. I think that is actually a worthwhile thing to do. Let me find the specific problems that I'm thinking of. Yeah, because I think we do actually put things in terms of kind of intersections, and it makes it I don't think we go quite as far into it as we could in the materials, unless you look across a few different lessons for it. So maybe starting from sort of scratch here. This might be a little bit redundant from what you've seen, but let's say we have A and we have B, right? So that's B, and then that's A, and this is some intersection that we see here, right? So if we're trying to consider the probability of, say, A given B, right? So if we're trying to consider the probability of A given B, then we want to think about this in relation to these two events. So the first thing that we're going to consider is, if we're thinking about this, if we're going back to our idea of the cardinality of A over cardinality of S, well, in this case, it's not necessarily the cardinality of A over the cardinality of S that yields a probability, or the probability we're looking for. We want to kind of think of a subset of A, which is going to, in this case, be the intersection of A and B, right? So instead of thinking about this, cardinality of A, we're actually thinking about the, let's think about it as the probability instead. The probability of A intersect B, right? So that's the first thing we're looking at. But we need to have some normalizing agent, right? We need to have something that against which we are comparing the probability of this, and that is event B in its totality, right? So that's going to be this intersection over all of this, and we can see that pretty clearly if we say the probability of B. So I think that's kind of nice. We can kind of see that pretty clearly. In this case, it's just the intersection over the totality of B. So we're looking at the probability of A intersect B over the probability of B. And it turns out that this is actually Kolmogorov's definition. So that is Kolmogorov's definition. And that's the probability of A given B equals the intersect of A with B over the probability of B. So that's kind of our starting point. And there's we can take this further, right? We can start thinking about the composition of a single event as being built out of disjoint events of which we don't necessarily have all the information at hand. And maybe a way that we can visualize that is, or one way I like visualizing it, at least, is let's make, we'll just do the same thing. Here's S. We'll define A. So that's event A. And let's divide this into parts. So we're dividing A into parts. We're also dividing S into parts. And so we've got A, and then, so A is this circle, right? And then we've got B1, B2, and B3. And B1 is, the entirety of this area. And B2 likewise for the other area. So let's say we don't know, we don't understand the event A by itself. If we wanted to compose A, we could do this, sort of step by step with, just looking at these, right? So A, this section over here of A is actually the intersection A and B1, right? So that's that part. And over here, this part of A is A intersected with B3. And this part of A is A intersected with B2. So if we want to compose A, we can do it just like that. We can just say that is, I'll just draw this on a clean sheet and we'll go from there. A intersect B1 plus A intersect B2 plus A intersect B3. Okay? So that is A. A is composed of that. So, you know, that's a starting point. We can go, oh, I'm sorry, I'm doing addition here. I'm kind of mixing my operators. And just to be very clear, what I meant to put there is union, actually. So these are all unions. And that makes sense, right? So we're unioning all these parts of A. And those parts are just the intersections between A and the specific region of S, B1, B2, and B3. So we can, let's go back to Kolmogorov for a second, right? We've got this probability of A given B being equal to the intersection, the probability of the intersection of A with B over the probability of B. We can rearrange this, okay? So I can multiply both sides of this by the probability of B. And that allows us, sorry, let me mute my other computer here. Slack keeps clicking at me. Okay. And so this leaves us with the probability of A intersect B multiplied by the probability of B being equal to the probability of A given B. And, you know, this might be leading to something clicking a little bit, right? We can now rebuild this composition of A in terms of probabilities based on this, and you know we can do that pretty easily, I think. So let's do that. If we're considering the probability of A given B, we can kind of recompose this, right? I think pretty easily at this point. We can also rewrite this a little bit further. Sorry, let me just rewrite that a little bit further as oh, did I write that backward? I think I did. Let me step back. Okay, let's start at Kolmogorov's again, because I think I swapped A given B with A intersect B. My mistake there. This is the probability of A intersect B over probability of B, right? Multiply both sides by probability of B. Yeah, I totally did, didn't I? Yeah. Okay, so what we get out of this is A intersect B is equivalent to the probability of A given B multiplied by the probability of B. Okay. This is this is the thing that allows us to move forward. Apologies for that. Okay. So with that, we can rewrite this composition of A in terms of probability, and that's going to be helpful for us. It just, you know, it's an easier notation from which we can build everything that we're trying to build. So in this case, you know, we're going to make it slightly more complex than just probability of B because we've got B1, B2, and B3. But you'll see that this kind of works. So if we talk about the probability of A, so we're not thinking about this necessarily in terms of the intersections and unions anymore. We're thinking about this in terms of probabilities. We're going to see that, okay, A intersect B1 is going to be the probability of A given B1 multiplied by the probability of B1. We add to that the probability of A given B2 multiplied by the probability of B2. Add to that the probability of A given B3 multiplied by the probability of B3. So, we could do this with, if we this could be 2, it could be 3, it could be 20, right? Be 20, but this is a form that we can often work with. We often, for these problems, we're going to be given these probabilities, and if we can discern how to construct the probability of A from, if we can determine the workflow for filling in these probabilities, we can solve for law of total probability. So that maybe that's a little bit of a wormhole, I think, or a rabbit hole. Does that answer your question? What is A with actual operators? This is A with the actual operators, right? Like, so we're at this point we're asking probability, and we're looking at actual operators that are that we can just utilize, right? Multiplication. We're getting away from the set operations when we do this. So I think the big change we are seeing is this transformation of this kind of unusable form to this usable form, right? Like, what does this mean? A intersect B1. What does that mean? Just in a vacuum? Not much for our purposes. Not for these types of problems. So in the transformation of this, right, we're going from A to probability of A, and we're able to encapsulate this intersection as the product of two probabilities. So I think that's really helpful, right? That's our equivalent statement, that probability of A intersect B1. This is straight from Kolmogorov, is the same thing, is equal to the probability of A given B1 multiplied by the probability of B1. So this is the crux of it for total probability in that transformation. So hopefully that clears it up. The question is, when you're intersecting probabilities, you can just multiply them. Essentially. Essentially, that's what you're doing. But be careful. You're not just multiplying probabilities. You're multiplying a conditional probability with a probability, you could say. They're both probabilities, but ultimately you're multiplying them, and then you are summing them against the other components that you need to compose the probability of something, like in this case the probability of A. Cool. Hopefully that's helpful. And you're going to see that again in I think the last day of class before we start going over technical interview, sort of like competencies on the last day. But we'll do, we're going to cover, all of conditional, we're going to cover all our conditional probability materials, and then we're just going to do a bunch of problems, a bunch of worked problems. And most of those are just kind of straight out of a textbook type problems, sort of like the problem that I walked through a little bit from Learn. And, those are mostly going to have to do with Bayes' theorem. There will be a couple, just a couple law of total probability problems, but when we get into Bayes' theorem problems are actually total probability problems. Can we convert the last set to lines of code? Yeah, that's it. We can put it into a calculator, and that's kind of a strange thing about this, about conditional probability. It's the one class we do as a pen and paper class. All the other classes we've basically moved to being able to write almost everything out in Python. But what we could do, you know what we could do? We could do a couple more worked problems, if that would be helpful, because I don't think there are that many worked problems in our materials for conditional probability. I think we have a few Bayes problems, but let's see. We could do a classic problem. It's kind of the marble problem. Let me make sure that isn't already what's in that example. There are 3 urns, each filled with red and blue marbles. Urn 1 has 75 red and 25 blue. Oh my gosh, that is the same exact problem. Okay. Let me see if there's a different problem that we could do. Yeah, the thing about this is I have a bunch of Bayes' theorem problems in front of me, but we could probably rework these to be law of total probability problems. So why don't I do that? Why don't we do a couple of those examples? I think that could be helpful. Okay, so so this is again, this is a Bayes' theorem problem in this form. So there are 2 bowls filled with cookies. Bowl 1 has 20 vanilla cookies and 20 chocolate cookies. Bowl 2 has 30 vanilla cookies and 10 chocolate cookies. Given that a random cookie is taken from a random bowl and each bowl has the same probability of being chosen, what is the probability that the cookie comes from bowl number 2, given that it is vanilla? So let's rethink this problem a little bit and just consider what is the probability of choosing a vanilla cookie. So let's figure this out as we've got 2 bowls of cookies. I'll use color black. We've got 2 bowls of cookies. This is bowl 1. This is bowl 2. And in bowl 1, we've got 20 vanilla and 20 chocolate. And in bowl 2, we've got 30 vanilla and we've got 10 chocolate. So what we want to figure out here, instead of figuring out the question that I asked, let's just try to figure out the probability of choosing a vanilla cookie. That is the challenge. And that is really the crux of this problem. So if we want to figure that out, this one, there are a couple ways we could figure it out in this case, but the way we should figure it out is through the lens of total probability. So we're going to look at how many vanilla cookies are in bowl 1. Okay. We're going to do that. We're going to look at how many vanilla cookies are in bowl 1. And then we want to look at the probability of choosing bowl 1. So we're going to compose this with the probability of choosing a vanilla cookie from bowl 2 multiplied by the probability of bowl 2. And so in that light, this shouldn't be, I think this is a little more obvious, how we're thinking about the law of total probability. We could we can answer a lot of these questions. We can answer the question, what is the probability of vanilla given bowl 1? That's going to be 0.5, or 20 out of 40. What's the probability of bowl 1? Well, as we established, the probability of bowl 1 is the same as the probability of bowl 2, which is 0.5. What is the probability of vanilla given bowl 2? Well, that is 30 out of 40, so 0.75, right? And with that information, we can kind of just fill these in. Vanilla given bowl 1 is 0.5, bowl 1 is 0.5. Vanilla given bowl 2 is 0.75, and bowl 2 is 0.5. So that's answerable. If we plug that into a calculator, 0.25 times 0.125 times 0.75. So that should be 0.625. Okay, so the probability of vanilla is 0.625. Oh, shoot. Now, why did we have to go through all of this when, maybe you're noticing that, well, what if we just divided 50 by 80? What would we get? We get 0.625. Here's the catch. That's fine. That works as long as bowl 1 and bowl 2 have equal probability, or equal weight, as it were, right? But what if we change those values? What if we imagine bowl 1 to be a much larger bowl, and we can rethink this problem sort of based on that idea? So all of this is going to stay the same. What's going to change is this probability of bowl 1 and probability of bowl 2. Let's say that bowl 1 is much more probable, right? So bowl 1 is going to have a probability of 0.9, and the probability of bowl 2 is going to be 0.1. So just imagine bowl 1 is this huge bowl. We're more likely to reach into it. It still has the same number of cookies, or the same frequency of cookies, we could say. And bowl 2 is much smaller, so we're less likely to reach into it. And if we kind of work through this again, that's 0.5. This is 0.75. Bowl 1 is 0.9, and bowl 2 is 0.1. And if I throw that into a calculator, we're going to get a very different answer, right? Let me make sure I can see this. 0.5, 0.9, 0.75, 0.1. So 5 times 0.9 plus 0.75 times 0.1. In this case, we get a different answer, right? What we're seeing is a reduction in the probability of choosing a vanilla cookie, right? And if you think about that, it kind of makes sense, right? In this case, probability of vanilla equals, what was that, 0.525, I believe? Yeah. So in this case, there's more weight of vanilla in bowl 2. There's also more weight of vanilla overall, but since bowl 2 has been vastly reduced in its weight, the effect of this 30 out of 40, this 0.75 probability for vanilla, has been lessened in the overall composition. And so what we see is a reduction in the probability of choosing a vanilla cookie overall. It's sort of moving toward this 50-50, right? And you can imagine it would be even more dramatic if we said 0.99, 0.001, right? We're going to be getting closer and closer to this 50-50 that we're seeing in bowl 1. The question is, this is essentially the same problem we just worked through, just with easier values to digest? Yeah, totally. Yeah, it's funny. there are these tropes in probability, like dice and coins and bowls with cookies and urns with marbles, and I think it is helpful to do those kinds of problems, right? Because in this case, you can imagine you close your eyes, you reach out, and one of the bowls is really big and one's really tiny. You're more likely to choose from the larger bowl, right? And so the larger that bowl is, the more weight or the more effect that's going to have on the composition of the final probability, right? If and the probability that or the frequency of something that we're seeing, like the frequency of vanilla here is going to be much more important than the frequency of vanilla over here. We could switch that around, of course. Like instead of bowl 1 being 0.999, maybe bowl 2 is 0.999 and bowl 1 is 0.001, and we're going to see that move, right? We're going to see that kind of invert in a way. So that would be 0.5 multiplied by 0.001 plus 0.75 multiplied by 0.999, and we're going to be very close to 0.75, right? Because the frequency of vanilla in bowl 2 is going to end up dominating, because bowl 2 is going to have such a heavier weight. So I think it's also helpful to just play with the numbers on these. Once you have a problem that is reasonably understandable, like this cookie, vanilla and chocolate chip cookie bowl problem, this type of problem, if you start playing with the values, then you start getting a much better intuition around this, and you start seeing that there's two weights happening. There are two weights that we're considering. We're considering the weight of vanilla. We're also considering the weight of the bowl. And this same idea applies to any phenomenon where we're approaching conditional probability in this way. Okay, so let's think of, we can kind of, I think we can kind of stick on this type of problem a little bit. And, this is for those of you in Premium Prep, this will be a preview, somewhat of a preview for the conditional probability day. But I think that's a good thing, I think Bayes' theorem and conditional probability tend to be pretty difficult for a lot of people. And so we can kind of stick on some of those, I think. So let's look at one more problem, and this will actually be a Bayes problem, but it'll have a it'll have a law of total probability component to it, which, most Bayes problems really are fundamentally law of total probability problems. So I think this one's kind of fun. It's a little bit of a brain puzzle. It is, so I've got it up here, and I'll try to, have that be sitting there reasonably. So let's think about this. Freddie remembers to take his umbrella with him 80% of the days, and it rains on 30% of the days when he remembers to take his umbrella, and it rains on 60% of the days when he forgets to take his umbrella. So what is the probability that he remembers his umbrella when it rains? And I think it's kind of fun because it implies a certain kind of causal relationship, right? Like nature is answering to Freddie taking his umbrella or not, which is a pretty unreasonable assumption, but we'll go with it. So the first thing that I think it's good to do with these problems is just write down what you know, write down what you can observe, and I'll move this down here for the moment, and I'm just going to hide the Bayes theorem for a second. We'll come back to it. So when we're thinking about this, well, what do we know? He takes his umbrella with him 80% of the days, right? So that's the probability of umbrella is going to be 0.8. And it rains on 30% of the days when he remembers to take his umbrella. So 30% of the days when he remembers to take his umbrella. So there's sort of this contingency here. So rains given umbrella, right? The probability of it raining given he remembered his umbrella is 0.3. And then the probability of it rains on 60% of the days when he forgets to take his umbrella. So that's very similar. It rains given not umbrella, right? It rains 60% of those days. And then what we're really asking at the end of the day is what is the probability that he remembers his umbrella when it rains? So what we want to ask here is something concerning with umbrella given rain. So the probability of umbrella given it's raining. And when you see this, notice the universe we're working in, right? The universe we're working in is this universe of rain. That's what we are considering. And so when we're building our total probability in relation to this type of question, that's what we're considering. We're trying to figure out the probability of rain. And the question is, can we do that from the information we have here? It turns out we can, but we need to fill in some more information. So what we have here, probability of rain given umbrella and probability of rain given not umbrella, well, that's pretty helpful. We have the probability of umbrella, but notice we also need to think about the probability of not umbrella. Well, if we have the probability of umbrella, the complement is the probability of not umbrella, right? So we can just, basically say probability of, I'm just going to put an overbar there for lack of room, that's going to be 0.2. So with that, we have all the weights we need to compose the probability of rain. And the probability of rain is going to be the probability of rain given umbrella multiplied by the probability of umbrella. And we add to that the probability of rain given not umbrella multiplied by the probability of not umbrella. So we have all of that. We have everything we need to do this. And probability of rain given umbrella, that's going to be 0.3. Probability of umbrella is 0.8. Rain given not umbrella is, I wrote down 60. Oh, 0.6. I'm like, okay, great. 0.6. Probability of not umbrella is going to be 0.2. Okay, so we can figure that out pretty easily. I'll just throw that into calculator. That is going to be 0.3 times 0.8 plus 0.6 times 0.2. And I know it's hidden behind 0.3 times 0.8 plus 0.6 times 0.2. It looks like that is 0.36. And so at that point, we know the probability of rain, which is 0.36. That's not what the question's asking us. The question's asking us the probability of umbrella given rain. But at this point, we actually have all the information we need to solve this problem. And I'll just show you that because why not, right? So in this case, probability of umbrella given rain, if we follow the format of Bayes' theorem, this is going to be the probability of rain given umbrella, which we know, multiplied by the probability of umbrella, which we know, over the probability of rain, which we figured out. So let's fill that in. Probability of rain given umbrella, we know that as 0.3. Oh, I'll just do it there. Probability of umbrella is 0.8. You can see it there. And probability of rain is 0.36, I think, is what that was. Let me just move this out of here. Yeah, 0.36. And at the end of this, well, we can just throw that into a calculator and find out. So that is 0.3 times 0.8 divided by 0.36. That looks like 2/3 to me, or 0.667, we could say. Like I said, after you do a few of these, they sort of systematize, and I think that's pretty helpful. If you just run through a few of these, I think it's also nice to change the story. Okay, so in this story, and this is a strong recommendation I'm going to make. I'll just demonstrate what I mean. Okay, so here's our story. Freddie remembers to take his umbrella with him. Let's say, I don't know. Derek remembers to take his, how about to feed his cat? Derek's not a very good cat parent, 80% of days. About, the cat meows a lot on 30% of the days when he remembers to feed it. And on 60% of the days when he forgets to feed it. What is the probability that he remembered to feed his cat when the cat meows a lot? And we can change those numbers, right? So maybe he remembers to feed his cat. Let's make him a little bit of a better pet owner. Let's say 85% of the time. Cat meows a lot on 20% of the days when Derek remembers to feed it. And on 60% of the days when he forgets to feed it, let's do, just 65 or something. What is the probability that he remembers to feed his cat when the cat meows a lot? So this is the same exact problem, different story. It's not much of a move away from the original story, but I just want to point out that you can always do this. You can always take, especially with these conditional probability problems, you can go out and find some, but I think it's often really helpful for building your own intuition if you author some yourself. I recommend that for distributions problems as well. I think it can be really helpful. So I'll just put that in the Slack. I'm not going to solve it. It's the same procedure to solve, but feel free to solve it, and feel free to use these kinds of problems as templates to write more problems. Okay. So, yeah, if there are no other questions, I might start exploring, sort of doing some exploratory coding, but I can move away from that at any point if somebody wants to drop a question. So, I kind of want to harken back to that binomial sampling problem. And I want to construct a new, a sort of new distribution. so this was the problem where we get a bit, we build a list of bits, and we build this binary sampling dictionary. At the end of it, we get, we're essentially defining a binomial process, and what we're getting out of that is a representation of a binomial distribution with a probability of 0.5. So, and a number of trials of 8. So that's a that distribution is something that is studied, it's known, but what about distributions that we're not familiar with? What about distributions that we don't know? And really, what about distributions that we invent? So I'm just gonna invent something here. Let's get. I don't need to write a function for this, but let's get a random number. So from random, I'm gonna import rand int, which I don't use too often, but why not? Let's play around with it. Let's say get n random numbers, and we'll put a low bound and a high bound on that. The high bound will be inclusive, and we'll say we'll just make an output list, and I'll do this as an accumulator instead of comprehension. Let's just set this as, I'll just do out, and we'll say, number of digits. Let's do that. Yeah, I think this is fine. Okay, so for whatever in, let's default this to 4 numbers. Okay, so for whatever in number of digits, let's let's say out.append, and we'll append rand int, and I think we can just do low to high plus 1 if I'm not mistaken. We'll test that in a second. So we return out, and again, the goal of this is to demonstrate a phenomenon that we don't know, that we are defining. And let's say this low is 2 and the high is 12. So ideally, let's just find out. Let's see if this works. Run dummy.py. Int object is not iterable. Oh, that's because I need to do range. Okay, 8, 3, 4, 4. That isn't too surprising. 10, 5, 13, 7. Oh, wait a minute. Interesting. Okay, so rand int, this high value, it looks like that is already inclusive in rand int. So as we saw, well, you know what? Let's run this a couple more times. 12s. Yep. Okay, so when I had that as 13, it included 13. Either way, easy fix, and we've got this function. So let's go from there. Let's consider summing the even numbers and subtracting the odd numbers. Okay, yeah, let's do that. So we'll call this process nums, and why don't we just pass in a num list, sort of like what we just defined. And what this is going to do is it's going to any even numbers, it's going to add to our sum. Any odd numbers, it's going to subtract. So for num in num list, if num mod 2, then that means that it's odd if this evaluates to true. If num mod 2, then sum is going to be reduced by 1. Is going to be reduced by the number. Otherwise, sum is going to be incremented by the number. And we can return the sum. Okay, so let's test that. and we'll process some nums. Oops. Process nums of that, where low is going to be, let's do 2 and 12, why not? And we'll print that result. So 2, negative 13, 8, negative 8, negative 10, negative 28, 19, 5, right? So if we want to get an idea of the distribution of these numbers, an easy way to do that is through a dictionary. So we've created a phenomenon, and we don't really understand it yet. Let's look at this through a dictionary and see where we get with it. Okay. So let's call this. Just call it num dictionary, and we're going to just set a number of samples. You know what? We'll do number of samples is 1,000. We'll do a low and a high, and I think that should be good. Okay. All right. So we're going to define a dictionary, and maybe I'll just give a little more space here. We're going to call out to process nums. Probably should have just copy and pasted that thing I had before, but that's okay. Process nums on this get n random nums. We've got low and high. We need number of digits. So number of digits. And we'll just do 4 by default. So this distribution, offhand, I don't think is named. I don't think this is a distribution that is a studied thing out in the world, but it doesn't have to be. Okay, you can create distributions. You can create things, and let's just fill this in. So this is kind of a bit boilerplate, really boilerplate in that. There's kind of a template of code that we can just adapt for this kind of problem. So I'm just gonna say for whatever in range, and we'll do num samples. And what I can do here is get this sample. And then I'm going to see if sample is not in the dictionary, then d sub samp is going to get that sample, is going to, how should we do this? Let's do it like this. Let's set it to 0. And in every case, we'll increment that. This is that syntax that I like using. And we'll just return the dictionary. And now we can analyze this phenomenon. So I'll just set low to 2 and high to 12, just to kind of stick with the same theme. And we'll get out of this a dictionary, and then we can traverse through this and take a look at what these values look like. So I'll just say for key value in d.items, we probably want to sort this because this is a sampling approach. So they'll be all out of order. So it'll be easier if we can read through from the lowest to the highest numbers. We can print an F string of key and the value. Okay. So let's take a look at this. All right. So it might be a little tricky to figure out, to really describe this, this offhand, honestly. Let's see. Let's change this to 2 digits. Yeah, because what I'm thinking here is what is going to be our lowest number? That should be, if it's odd, I think that should be all 11s, which would be negative 44. I wonder if we ever get a negative 44 in here. I think we probably do. Okay. My suspicion here is that we're not doing anywhere near enough samples to get a clear idea of the distribution. So maybe we need to do more samples. You know, let's do 100,000 instead. And something that stands out to me is that we have this sort of alternating frequency a little bit, and we have certain numbers that are a lot higher than other numbers, like 0 and -2, -4 and 2. So we have this kind of bumpy thing happening, which I think is kind of neat, right? And I think that is a byproduct of that evens get added and negatives get subtracted. Sorry, even and odds get subtracted. And of course, once we get out here in the wings, the frequency of these occurrences is a lot less, which I don't think should be too surprising. So the highest number we can get is 44. Oh, am I adding? No, I'm subtracting. I'm subtracting evens. Okay. Right, because this is going to be, let's see, 2 12s and 2 10s likely. So even still, we're not getting the maximum value that we can from process nums, which I think is kind of interesting, right? We're sampling 100,000 times and we're still not getting it. But let me just print. If we were to get a 12 and a 12 and a 12 and a 12, I think that's fairly unlikely. That's, oh, we want to process those nums. Yeah, so the most we should be able to ever get is 48, and the least is going to be, you know, as I said before, this least number. This is all our all of our 11s. So that should be a -44, which we do see. So even in 100,000 samples, you know, we're not generally getting that, but we can look at this sort of thing and start determining things about the distribution. I think it might be easier to put these into buckets and look at it. I think also, you know, trying to determine why certain outcomes are more likely. I think that is that's an interesting exploration. I think it's probably a simple number theory thing. Anyway, this is, you know, the reason I'm getting at this is that there are a lot of problems that look like this that we ask. The technical interviews in general have a problem that kind of fits with this idea. Not this specific problem, I just kind of made this up, but I want you to be aware of how to go about exploring these kinds of things. So with that, let's, there's another problem that came in the Slack. There's a question here about how to translate an inclusion-exclusion principle problem into code. Yeah. See, this is the thing with these kinds of problems, and maybe I'll just I'll look at this. What I'm going to suggest is these kinds of problems are not that conducive to code, and I really need to think about this more, because I've been wondering about this, say, with conditional probability. Like we teach conditional probability pen and paper, and that's not to say that there aren't ways to put that into code. It's just those ways aren't particularly useful in relation to they're not particularly useful in relation to these kinds of textbook problems. And I know that's not a very satisfying answer. Trying to think of I mean, I think you could do a fairly intense if you feed in the set notation, maybe you could parse that with Python. I've done this before with say derivatives problems, where it's just kind of a fun exercise to write functions that take derivatives or provide integrals. And but at the end of the day, you're sort of procedurally processing. You have to like procedurally analyze a form of the equation that's passed in order to provide the derivative or to take an integral. And I think that though that's cool and it can sort of concretize the process of it, I think that's what you're looking at. You're looking at more of a text processing approach, if that makes sense. I can post this code for sure. Yeah, I don't like agreeing with the statement. Sometimes it's easier on paper than with Python, because but I do think I think there are exceptions, and I think of when I think of inclusion exclusion principle, when I think of conditional probability, I think of those as not being that easy to represent effectively in Python or more intuitively in Python. Whereas in things like the discrete distributions, I feel like those lend themselves very well to Python, right? Because we can use these sampling processes and counting processes, especially the ones that we cover, binomial Poisson and geometric, or the ones that we cover more deeply. I think in those spaces with those it's easier to express those statistical or those probabilistic concepts in code than it is to do so on paper. But I'll have to think about inclusion exclusion principle, because maybe I'm overlooking something. There might be something in there that we can pick apart. I'll think about it and play around with the idea for a little bit. There's a question in the code for KV in sorted d.items. It is traversing across a list containing tuples. Yes, and we can see that. This is if you're ever wondering about this, you don't have to put this into a for loop. We can actually print the sorted version of d.items and see that explicitly. So this looks exactly like a list of tuples, and if we run type on it, so type is going to tell us it's a list. If we get rid of the sorted, though, notice that it's a dict items. It's a dictionary items object. But if we look at that, it is list-like, right? Sorry, let me print that. If we print that, it is going to be list-like. So I think we can still think about it like it's a list, but notice it is, this list that's in here is actually wrapped by the dict items object. So it's list-like. When we pass into sorted, sorted returns a list. So we're actually converting this into a list when we sort it, if that makes sense. But for our purposes, it operates pretty much exactly like a list containing tuples either way, whether or not we sort it. But technically, this is not a list, it's a dict items object, but it's basically a list, right? Like a list with tuples in it. If we, for some reason, wanted to sort the dictionary based on the value, not key, but return both the key-value pair, what's the most efficient way to do that? The most efficient way to do that, I always have to kind of look this up. So if you Google Python sort dictionary by values, you'll probably find a quick Stack Overflow thing. I have to look this up because it's just a syntax that I don't remember offhand. But it does utilize sorted, actually. So let me paste this in. This is we're performing a lambda to sort. So notice in sorted, X should actually be D here. Sorted has the option of setting our item to be sorted as the second item. That's what's happening here. So this syntax is probably the best way to do this. And if we want to output this into a new dictionary, which I think we're doing here, let me just make sure that that's what we're doing. I think in this case we are swapping. Well, let's find out. I might be wrong how I'm thinking about this. Let's find out. No, we're still looking at the same dictionary. Let's do this instead. Let's try that. Okay, that's better. All right. So in this case, what we're doing is we are sorting by value, right? And essentially, there's just this parameter right here, right? This parameter key, where we can set essentially kind of an anonymous function that will end up sorting on the second item. The second part of the item that is in the dictionary. So item is kind of this key value pair. Item sub 1 is going to be the value. So we're sorting on the value in this construction. So that is the best way that I know of to do this. There's a longhand way we can do this, but that's essentially writing a function that just inverts the two, right? That inverts the keys and the values, and then sorting on the inverted form of that. But it's good to know this syntax, it's good to know that the syntax exists. I always look it up because I forget it, but yeah, that's basically it. Yeah, and like a really great thing about programming is that somebody has figured out how to do what you're trying to do, and one of the, I've been programming since I was 12 and professionally for somewhere around 20 years. And what you realize pretty early on is that you can't remember very much, let alone remember everything, but you can't remember very much in terms of syntax. And often the way to deal with that is having a notes document for the specific language, or just for the domain that you're working in, especially when you get into like if you get into AWS or GCP, especially AWS, right? You kind of have to Google everything. You have to traverse their documentation, and you're going to spend a lot of time on Stack Overflow. They also update things all the time, and so you know how to do something one day, 2 months later, 2 months later, the way that you knew how to do that thing doesn't work anymore, and you have to update the stuff that's there. So you kind of live and die by Google, and you also live and die by your own documentation. The stuff that the notes that you take. There's a video I have somewhere. Well, it's on our channel, but just going through if you're in the process of learning something, especially in the process of learning something, like you start a new job somewhere, and maybe there are new technologies you're using. I think it's nice to have a single text document, markdown document, where you keep all your new notes, and you open that thing up and you just paste indiscriminately into it, and you try to have reasonable descriptions, and you just try to keep everything there. And so between Google and that document, you keep your head above water in the most inundating times of, say a new job or a good, the reason I made that video is I think that's exactly the right thing to do when you're in the DSI. Have a single text document and put everything in there, right? I say everything, I don't mean everything, but having archetypal examples of everything is really good. Like, having a couple Bayes theorem worked problems in there so that you can use those as templates for other things. Having, functions that demonstrate certain algorithmic patterns, I think that can be very helpful. And the nice thing about Markdown is you can also do mathematical formula in there, so that ends up being really helpful as well. But yeah, never be afraid to Google stuff. Except in the technical interview, you can't Google anything. You can ask us. But in general, just Google's out there, and we're always going to forget even basics. It's really humanizing when you realize how little you can remember at any given moment in the domain that you're actually working in, which is, I don't know, maybe we need to forget in order to experience this world. I don't know, but one nice thing is we have external memory that we can reference, so that's always helpful. Cool. That's me for today. If you have questions, reach out by Slack. We'll do our best to get back to you. If you're in Premium Prep, I'll see you all on Monday. I think we're starting discrete distributions on Monday. And no, actually, we're starting analytic approach, which is kind of a precursor to discrete distributions. It's going to look a lot like, the sort of stuff, this sort of code, but with, other problems. And don't hesitate to reach out if you get stuck on stuff. And yeah, it's been a pleasure. Thanks so much, and I will see you all soon.